Hello. Welcome to this presentation on the TRINEFLEX project outcomes. Today, we are exploring the Aeration optimization service implemented for the Esamor wastewater treatment pilot in Spain. Presented by Aidna, this session covers how we integrated energy and process flexibility to transform an energy-intensive industry. We will discuss how our predictive strategy allows the plant to transition from reactive to proactive management, optimizing blower operation to minimize costs. Let's get started. Moving to the model objective, our strategy is built on three main pillars. First, energy consumption minimization, where we aim to optimize blower operation by identifying the minimum necessary airflow to reduce energy use and costs. Second, we ensure water quality compliance. The model is designed to keep effluent parameters, such as pH, DQO, and ammonium, within acceptable regulatory and operational ranges at the outlet of the aeration process. Finally, we employ a predictive operational strategy. This involves 10 specialized models that predict key variables, including nitrogen, oxygen, and redox potential. This approach allows us to transition from reactive to proactive plant management. Why is this service so critical? Aeration is the single most energy-intensive process in the plant, making blower optimization the most direct path to reducing operational costs. The real challenge lies in finding the minimum operational point, the exact level of airflow that maximizes energy savings without risking a violation of regulatory limits for water quality. By moving away from manual toward an automated, AI-driven decision support system, we are transitioning the Esamor facility into a true Industry 4.0 operation. Now, let's dive into the model architecture, which is the core engine of the entire service. We have developed a two-stage hybrid framework that bridges the gap between high-level deep learning and practical industrial mathematics. The first stage is our GRU-based predictive layer. This architecture is designed to look at a rolling window of the last 60 minutes of real-time SCADA and laboratory data. From this, it generates a high-resolution forecast for the next 60 minutes, tracking 10 key process parameters, ranging from nutrients like ammonium and nitrate to physical factors like compressor temperature and suspended solids. This brings us to the second stage, the constrained optimization engine. Instead of just predicting the future, this engine acts on it. It takes those 10 forecasts and runs them through an aeration effluent quality model. By adjusting the controllable variables, specifically the sulfur, the engine identifies the absolute minimum airflow required that still satisfies every single water quality constraint. Finally, for DSS integration, the model is flexible. It can output these optimal set points in intervals of 15, 30, or 60 minutes, ensuring the plant's decision support system always has the most efficient instructions ready for execution. Now, let's examine the specific inputs that drive our forecasting engines. The system integrates three distinct streams of data to ensure accuracy. First, we ingest high-frequency operational data from the SCADA system, covering physical variables like sulfur flow and dissolved oxygen. This is fused with laboratory data, providing critical chemical parameters such as pH and suspended solids that are measured manually. We also incorporate temporal features, including cyclical time encodings, to help the model recognize and adapt to the plant's periodic patterns. As you can see in the diagram, all this information passes through a specialized pre-processing and fusion layer. Here, we handle missing values through interpolation and scale the data before it enters the GRU models to generate our 1 hour ahead predictions. Now, let's look at the specific inputs required for the optimization model. This engine works by combining the 1 hour ahead forecasts from our GRU models with the plant's real-world process constraints, such as strict effluent limits for pH, nitrogen, etc. The engine evaluates our controllable variables, primarily the sulfur flow, which is the main driver of energy consumption. It also considers sludge recirculation, though this typically remains near constant. By weighing these forecasts against the quality and operational limits, the optimizer determines the exact set point needed. So now, let's look at the concrete results delivered by the service. The system generates two distinct categories of outputs. First, the forecasting outputs provide a high-resolution look at 10 key predicted variables, including dissolved oxygen, redox potential, and suspended solids, for the hour ahead. These forecasts are the engine for our final stage, the optimization outputs. The mathematical model calculates the precise sulfur flow and sludge recirculation set points required for the next operational interval. By focusing on sulfur our primary driver for energy use, we achieve the ultimate goal, minimizing energy consumption and costs while ensuring that effluent quality remains 100% compliant with every regulatory constraint. Finally, let's look at how this service is integrated into the TRINEFLEX platform interface. A key feature for the user is the ability to select the resolution, which defines how often the system generates new optimal values for our control variables. As you can see in the dashboard, the system is currently configured to offer intervals of 15, 30, or 60 minutes. This flexibility allows the user to balance the frequency of set point updates with specific operational needs. Once we have selected the resolution and executed the simulation, the TRINEFLEX dashboard presents the final results in a highly detailed and actionable format. On the left, you can see the optimization results broken down into specific time blocks. For each interval, the system calculates the optimal set point for the blower and provides the estimated energy consumption in kilowatt-hours. For instance, it identifies exactly how much airflow is needed to keep the process stable while minimizing the energy footprint. To the right, the platform displays real-time forecast charts for both biological parameters and effluent quality. These visualizations track key indicators such as ammonium, nitrates, pH, and DQO. To finalize the results, the TRINEFLEX dashboard provides interactive visualizations for both biological and effluent parameters. Because these variables often operate on very different scales, the interface allows users to click the legend to isolate specific variables of interest, such as oxygen levels or pH. This capability ensures that the user can clearly verify, in real time, that the optimized set points are successfully keeping all water quality parameters within their mandatory regulatory limits. To wrap up, the Aeration optimization service successfully demonstrates how AI can drive both economic and environmental sustainability. By precisely balancing energy reduction with strict water quality compliance, we have moved the SMR facility into a proactive, Industry 4.0 operational model. This tool, developed as part of the TRINEFLEX project, provides a scalable blueprint for the future of wastewater treatment. On behalf of IDNA, thank you for your attention.